All right, so part two, we only have a couple more to graph. So, example, let's do a rational. Sketch f of x is equal to x minus 4 all over x plus 1. So 1, the domain of f. Well, what we know is the bottom can't be 0, so it's going to be minus infinity to negative 1, union negative 1 to infinity, and we know from pre-calc that negative 1 is vertical asymptote. That's why it doesn't, the domain doesn't exist there. 2, its derivative. Well, f prime of x is going to be the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So this is going to simplify to x plus 1 minus x plus 4 all over x plus 2 squared. So this is going to give us 5 all over x plus 2 squared. So that's f of x. F double prime of x. Well, since this actually is a constant, we can totally do the quotient rule again, but you could skirt the quotient rule by using the chain rule here. So I'm going to do it both ways to show you. So derivative of the top times the bottom minus the top times the derivative of the bottom, so 2 times x plus 2 to the 1, all over the bottom squared. So this is going to be equal to minus 10 over times x plus 2, bottom squared, that should be 4, all over x plus 2 to the 4th. So this is going to simplify to minus 10 all over x plus 2 cubed. And if we did it this way, f double prime of x would be equal to minus 10 times x plus 2 to the minus 3 times the derivative to the side, which is 1, which gives us that exact same thing. So the reason why we can do this is because the numerator was a constant. So you can just rewrite it like that. Okay. 3. What to do with 3? Let me make sure. Well, usually what we do is, before we do 3, I'm going to talk about it, but what we want to do is we want to find our critical values. Let's make sure, because that's usually what we do. Well, 3 is critical values. That's good. So number 3, we're going to do the critical values. So I'm looking for when f prime of x is equal to 0 or undefined. Now I'm putting the undefined in here because this is no longer a polynomial, so this is a possibility. So when I want to find the derivative is equal to 0, I have 5 over x plus 2 squared is equal to 0. And multiplying both sides by the denominator, I have 5 is equal to 0, so no solution. Which means there's going to be no local mins or maxes. For this one, it's undefined. We know a function, the derivative would be undefined is when the bottom is equal to 0. So this would be, for undefined, this would be when x plus 2 squared is equal to 0. So when x is equal to negative 2, so square both sides. Now, I don't know how I changed it, but this should be a 1. Just wondering what happened here. It doesn't change any of our work though, just so, except right here. So this is when x equals negative 1. Now, we know that it's going to be undefined here because it's not even in the domain. So it's not in the domain, so it's not going to be differentiable there as well. So x equals negative 1, we'll see that that's going to be that vertical asymptote. That's why it's undefined there. Number 4. First derivative test. The only numbers we got here was this negative 1, so when we look at our negative 1, we're going to go from minus infinity to negative 1, and then we're going to go from negative 1 to infinity. And I'm going to pick some x values. So x, I don't know, negative 2. For here, 0 because I can. and I'm going to plug it into f prime of x. So plugging it into the derivative, which is right here, this is going to be, actually this is going to be kind of nice. When you plug it into here, when you plug in -2, the bottom becomes -1. -1 squared is 1, so this is going to spit out 5. So f prime of -2 is equal to 5. If you plug in 0, it's going to be 5 again, yep. So f prime of 0 is also going to be equal to 5. Just plug it into this. So what I can see is that it's increasing, because this is positive, it's increasing, it's positive. And over here, this is negative, so this is also positive, so it's increasing as well. That's why we didn't have any local maxes or mins, because for that to happen, you know, it has to, these have to change signs. It's got to switch from increasing to decreasing, or vice versa. All right, number 5. Flexion points. Now, I'm going to treat this the exact same way as the first derivative. The inflection points will happen when the second derivative of x is equal to 0, but we still need to, so this is actually a point on the graph, but there are locations to where the where it can change concavity, and it can change concavity when it's either equal to 0 or if it's undefined. So we treat it just like the first derivative test as well. So we find where it's equal to 0 or undefined. We didn't do these in the other ones because they were polynomials, so this wasn't an option. But rationals, you have to do that for the first derivative test. You have to know where it's equal to 0 or undefined and cut it there. Second derivative test, if I'm testing concavity, you have to do the exact same thing, except now you're plugging things into the second derivative as opposed to the first derivative. So when f double prime is undefined, remember this is when I had minus 10. Remember this is when minus 10 all over x plus 1 cubed would be equal to 0. And again, since I multiply, this is minus 10 is equal to 0. So this has no solution. So there are no inflection points. But this expression here would be undefined when x plus 1 cubed would be equal to 0. The bottom is 0. So this is when x is -1. So we're still going to have to test concavity, and that -1 is a possibility where it might change from concave up to concave down, or the other way. So picking an x value, let's go -2 and also 0. Now testing concavity means second derivative. So f double prime of -2. So plugging -2 into here. Well, -2 gives us -1. -1 cubed is -1. -10 over -1 is going to be positive 10. So this is positive, so I forgot to write the intervals. So minus infinity to -1, and then this one is going to be -1 to infinity, so these intervals here. So it's concave up on that interval, and f double prime of 0 is going to be equal to plug in 0. This is going to be 1 cubed then, so this is going to be -10, so this is negative, so it's concave down. Asymptote. We have a vertical asymptote at the 0 of the denominator. So when we looked at the original function, which is this one, this has a vertical asymptote at -1, because that's when the bottom is equal to 0. So x equals -1. 7, let's, I'm going to do x and y intercepts here because there's so little information as far as points, and x and y intercepts of this are really easy. The reason why, what I mean by very little information is there's no maxes or mins, and there's no inflection points. The only thing I know is increasing, decreasing, and concavity. So that's why I'm going to do x-intercepts here. So x-intercept is when y is equal to 0. So I had x minus 4 over x plus 1. 0 would be equal to x minus 4 over x plus 1. So 0 would be equal to x minus 4. So x equals 4 is an x-intercept. And for y-intercept, this is when x is equal to 0. So y would be equal to 0 minus 4 over 0 plus 1. So y is equal to negative 4. So at least I had 2 points here. I have 4 comma 0, and I also have 0 comma 4. So graphing. So 0, 4, 1, 2, 3, 4, and 0, negative 4, 1, 2, 3, 4. I know that these are 2 x-intercepts. Right. We have a, forgot about the horizontal asymptote. Remembered for pre-calc, since the degree, well actually, we could just take the limit. Why don't you just take the limit as x goes to infinity? I like that better. Do I have enough room? Sure, why not? So y would equal the limit as x goes to infinity of x minus 4 over x plus 1. So dividing everything by x, this is the limit as x goes to infinity of x over x minus 4 over x all over x over x plus 1 over x. So what we're going to get here is this is going to be 1, this is going to be 0, this is going to be 1, this is going to be 0. So this is just going to spit out 1. So y equals 1 is our horizontal asymptote. So we have a vertical asymptote at negative 1, a horizontal asymptote at positive 1. All right, so going back to our information about concavity, what we know is increasing and concavity. From 0 to negative 1, it's increasing, and also from 0 to negative 1, it's concave up. So it's got to increase and be concave up in this over here. So the only way to do that to increase and concave up over here is it can't live in this one because that would be wrong. It'd have to be here. So it's got to increase and it's got to go concave up. Now over here it's got to decrease. Let's see, right? Yep. No, it's increasing as well, and it is concave down. So it's got to increase concave down. So for that to happen, it's got to look like that. So there's your function. I think we could have got away with not finding these, but might as well. Almost done. One more example. I'm going to do a trig function, so have a little bit of practice. All right, example. Given the first derivative. Okay, so I'm going to shorten this example. So let's say given the first derivative, so of y equals f of x, I want to find y double prime and use steps 2 through 4 of our graphing procedure, or sketching procedure. To sketch the shape. Okay, so I'm going to say y prime is equal to the tangent squared of theta. And this is going to live from minus pi over 2 less than theta less than pi over 2. All right, so 2 through 4. So step 2 was to find the first and second derivative. Well, I have the first derivative. So y prime is equal to the tangent squared of theta. And then y double prime. And y double prime would be equal to, well, the derivative of this is, remember that this is equal to the tangent of theta squared. So its derivative is going to be 2, this has to come out front, times the tangent of theta to the first power, multiplied by the derivative of the tangent of theta, which is equal to the multiplied by the secant squared of theta. So we get 2 tangent theta secant squared of theta. And if we want to clean this up to find like the numerator and denominator, what I know is this is equal to 2 times sine theta over cosine theta. And our secant squared is, this is 1 over the cosine squared of theta. So I can say 2 sine theta over cosine cubed theta. The reason why is I'm going to ask when this is equal to 0 and undefined, and it's easier to do it here. So remember, this is the same thing as the sine squared theta over cosine squared theta then. So let's find where this is equal to 0 and where this is undefined. So for this, so let's add f, but y prime equals 0 or undefined. So it's equal to 0. This thing would be equal to 0 when the numerator is 0. So this is when the sine squared of theta is equal to 0. So when the sine of theta is equal to 0. So going to our unit circle, that's what I beat the heck this semester. The sine of is equal to 0 right here and right here. Now we're only going from minus pi over 2 to positive pi over 2, so only right here. So that means 0. It's 0 right here. So this is theta equals 0. Now, it would be undefined when the cosine squared of theta is equal to 0. And if we want to know where the cosine is equal to 0, the cosine is equal to 0 at minus pi over 2, counting backwards, and also positive pi over 2. So from at negative pi over 2 and positive pi over 2, but they're not defined in our interval. These are open here. So theta is equal to plus or minus pi over 2, but it's not in our interval, so I don't have to worry about it. So what I'm going to do is I'm going to plug this into our second derivative. I'm going to see what happens. I'm going to see if this is a local max or a local min. So y double prime of 0 is going to be equal to 2 times the sine of 0 all over the cosine cubed of 0. At 0. I know the sine of 0 is equal to 0. We just showed that. So this is 0 over cosine of 0 is 1, so this is equal to 0, so it's inconclusive. So the test fails. I don't know if this is a local max or a local min. Probably an inflection point. 3. Now I know that the derivative is equal to 0 at 0, so when we do the first derivative test, we are going to chop it at 0, so the intervals are going to be minus infinity to 0 and also 0 to infinity. X values, let's do minus pi over 4. Minus pi over 4, let's do positive pi over 4. These are nice, pi over 4. These are nice values that are inside this domain. So y prime, so y prime of minus pi over 4 means I have to plug pi over 4 into here. So what we know is if we look at pi over 4, or negative pi over 4, right? If we look at minus pi over 4, the sine is going to be root 2 over 2. So this is going to be equal to, I'll show this work, root 2 over 2 squared, plug it in here, all over, that's negative, but it's going to become positive. And this is also going to be, on the bottom, is going to be positive root 2 over 2 squared, because that's what that cosine of negative pi over 4 is. So this is just 1. This is equal to 1, which is positive, so it means it's increasing. I'm also going to do y prime of positive pi over 4, and we can see that that's also going to be, it's also going to be equal to 1, because it's going to be positive root 2 over 2, positive root 2 over 2, so this is also going to be equal to 1. So this is positive, so it's going to be increasing. Next is second derivative test. So what I want to also do is we want to determine their concavity. So, oh, they only ask for 2 through 4. It's only 2 through 4. Let's see. I would love to know the concavity of these things. I know it said just 2 through 4, but we're going to look at the concavity as well. So y double prime equal to 0 or undefined. So when we look at y double prime, we know that this was equal to 2 sine theta all over cosine cubed of theta. And this is equal to 0, well, when the numerator is 0. So this is when 2 sine theta is equal to 0. So this is when theta is equal to 0. And it'd be undefined when the cosine is equal to 0. Cosine cubed is equal to 0, or the cosine of theta is equal to 0. And we already know that that's going to be plus, theta would be equal to plus or minus pi over 2. So not part of our domain, so I don't have to worry about it. So when we're looking at the domain, I know I'm just going to cut it at 0. So picking your x values, I'm going to still use that minus pi over 4 and that positive pi over 4, and then f prime of, f double prime of x, plugging that into our, remember, into our second derivative. So this is going to be equal to 2 times minus pi over 4 for sine is going to be minus root 2 over 2. All divided by the bottom is going to be cosine is going to be positive root 2 over 2 cubed, right? Now I'm not going to find the value of this. I'm just going to look at its sign. This is negative on top, this is positive on bottom, so this is negative. This is going to be concave down. Now if I plug this one in, this is 2 times positive root 2 over 2 all over root 2 over 2 cubed. All this is positive, so this is positive. This is going to be concave up. So we also remember the intervals that we just did that it's increase on this interval and also increasing on this interval. So just to remember that, this interval was increasing. It was the same exact to 0. And this one was also increasing. So when I go to look at the graph, I don't know its exact values. It didn't say to find them. It just says give me some shape. So I know it's increasing concave down. And this is going to be increasing concave up. So it's got to look like this. Increasing concave down has got to be something like this. And then it's going to be increasing concave up. That makes sense. Yeah, I can live with that. All right, so that's it for this. Long section, I know.